Hello all, welcome to this video on probability and distributions. Today I'll be talking about probability and random variable, discrete and continuous probabilities. Modern probability is based on three concepts of sample space, event space, and probability measure. The probability space models a real-world process referred to as an experiment with random outcomes. The sample space is the set of all possible outcomes of the experiment, usually denoted by omega. For example, two successive coin tosses have a sample space of HH, TT, HT, TH, where H denotes heads and T denotes tails. Event space is the space of potential results of the experiment. A subset of the sample space is in the event space if at the end of the experiment we can observe whether a particular outcome, which is an element of the sample space, is in this subset. The event space is obtained by considering the collection of subsets of sample space, and for discrete probability distributions, it is often the power set of sample space. With each event, we associate a number P of A that measures the probability or degree of belief that the event will occur. P of A is called the probability of A. The probability of a single event must lie in the interval 0 to 1, and the total probability over all outcomes in the sample space must be 1. In machine learning, we often avoid explicitly referring to the probability space. Instead, we refer to T as the target space and refer to elements of T as states. We introduce a function x which is mapped from omega to T that takes an element of the sample space and returns a particular quantity of interest, that is a value in T. This association or mapping from omega to T is called a random variable. For example, in the case of tossing two coins and counting the number of heads, a random variable x maps to the three possible outcomes: x of HH, which is 2, x of HT, which is 1, x of TH, which is 1, and x of TT, which is 0. In this particular case, T will be 0, 1, and 2, and it is the probabilities on elements of T that we are interested in. For a finite sample space omega and finite T, the function corresponding to a random variable is essentially a lookup table. For any subset S of T, we associate the probability to a particular event occurring corresponding to the random variable x. Now let us consider a statistical experiment where we model a funfair game consisting of drawing two coins from a bag with replacement. There are coins from US denoted by dollar and UK denoted by euro in the bag, and since we draw two coins from the bag, there are 4 outcomes in total. The state space or sample space of this experiment is then dollar dollar, dollar euro, euro dollar, and euro euro. Let us assume that the composition of the bag of coins is such that a draw returns at random a dollar with a probability of 0.3. The event we are interested here is the total number of times the repeated draw returns dollar. Let us define a random variable x that maps the sample space omega to T, which denotes the number of times we draw dollar out of the bag. We can see from the preceding sample space that we can get $0, $1, or $2, and therefore T will be 0, 1, 2. The random variable x can be represented as a table like given as following: x of dollar dollar, which is 2, x of dollar euro, which is 1, x of euro dollar, which is 1, and x of euro euro, which is 0. Since we return the first coin, we draw before drawing the second. This implies that the two draws are independent of each other. Note that there are two experimental outcomes which map to the same event, where only one of the draws return a dollar. Therefore, the probability mass function of x is given by P of when x is equal to 2, P of dollar dollar, which can be written as P of dollar into P of dollar. As we have already seen, P of dollar is 0.3. So the answer will be 0.3 into 0.3, which is 0.09. Then we take the case where P gives X is equal to 1, which can be written as probability of $euro union euro dollar, which can be written as probability of $euro plus probability of euro dollar. Since probability of dollar is 0.3, probability of euro will be 1 minus 0.3. So it can be written as 0.3 into 1 minus 0.3 plus 1 minus 0.3 into 0.3, which is 0.42. Next we take P of X is equal to 0, which is probability of euro, which can be written as probability of euro into probability of euro, that is 1 minus 0.3 into 1 minus 0.3, which is 0.49. Now we will look into discrete and continuous probabilities. Depending on whether the target space is discrete or continuous, the natural way to refer to distributions is different. When the target space T is discrete, we can specify the probability that a random variable x takes a particular value in T, denoted as P of x is equal to x. The expression P of x is equal to x for a discrete random variable x is known as the probability mass function. When the target space T is continuous, that is a real line R, it is more natural to specify the probability that a random variable x is in an interval, denoted by P of a less than or equal to x less than or equal to b for a less than b. By convention, we specify the probability that a random variable x is less than a particular value x, which is denoted by P of x less than or equal to x. The expression P of x less than or equal to x for a continuous random variable x is called the cumulative distribution function. Now we will look into discrete probability. When a target space is discrete, we can imagine the probability distribution of multiple random variables as filling out a multi-dimensional array of numbers. The figure here shows the visualization of a discrete bivariate probability mass function with random variables x and y. The target space of the joint probability is the Cartesian product of the target spaces of each of the random variables. We define the joint probability as the entry of both values jointly, that is P of when x equal to xi and y equal to yi, nij by n, where nij is the number of events with state xi and yj and capital N the total number of events. The joint probability is the probability of the intersection of both events, that is when P of x is equal to xi, y equal to yi, which can be written as P of x is equal to xi intersection y is equal to yj. The figure we saw here illustrates the probability mass function of a discrete probability distribution. For two random variables x and y, the probability that x is equal to x and y is equal to y is written as P of x comma y and is called the joint probability. One can think of a probability as a function that takes state x and y and returns a real number, which is the reason we write it as P of x comma y. The marginal probability that x takes the value x, irrespective of the value of random variable y, is written as P of x. We write x approximately P of x to denote that the random variable x is distributed according to P of x. If we consider only the instances where x is equal to x, then the fraction of instances, that is the conditional probability for which y is equal to y, is written as P of y given x. In machine learning, we use discrete probability distributions to model categorical variables, that is variables that take a finite set of unordered values. They could be categorical features such as the degree taken at university when used for predicting the salary of a person, or categorical labels such as letters of the alphabet when doing handwriting recognition. Discrete distributions are also often used to construct probabilistic models that combine a finite number of continuous distributions. Now let us consider two random variables x and y, where x has 5 possible states and y has 3 possible states. which is shown in the figure. We denote by Nij the number of events with state x is equal to xi and y is equal to yj, and denote capital N for the total number of events. The value Ci is the sum of individual frequencies for the ith column. That is, Ci is equal to sigma j equal to 1 to 3 Nij. Similarly, the value Rj will be the row sum. That is, Rj can be written as sigma I is equal to 1 to 5 Nij. Using these definitions, we can compactly express the distribution of x and y. The probability distribution of each random variable, the marginal probability, can be seen as the sum over a row or column. That is, P of x is equal to xi can be written as Ci by n. That is, sigma j is equal to 1 to 3 Nij by capital N. And P of y is equal to yj can be written as Rj by capital N, which can be written as sigma I is equal to 1 to 5 Nij by capital N, where Ci and Rj are the ith column and jth row of the probability table respectively. By convention, for discrete random variables with a finite number of events, we assume that probabilities sum up to 1. That is, sigma I is equal to 1 to 5, P of x is equal to xi is equal to 1, and sigma j equal to 1 to 3, P of y is equal to yj is equal to 1. The conditional probability is the fraction of a row or column in a particular cell. For example, conditional probability of y given x is P of y is equal to yj when x given as xi will be nij by ci, and the conditional probability of x given y is P of x is equal to xi when given y as yj will be nij by rj. Now let us look into continuous probabilities. A function f that is mapped from a d-dimension space to one-dimension space is called the probability density function, or PDF, if for all x which belong to the d-dimension space, f of x is greater than or equal to 0, and when its integral exists and when we take the integral with the lower limit to be r raised to d, f of x dx evaluates to 1. For probability mass functions of discrete random variables, the integral is replaced with a sum. Observe that the probability density function is any function f that is non-negative and integrates to 1. We associate a random variable x with its function f by p of a less than or equal to x less than or equal to b, giving integral a to b f of x dx, where a, b are real numbers and x is a real number, which are outcomes of the continuous random variable x. States x, which belongs to the d-dimension space, are defined analogously by considering a vector of x, which is a real number. This association is called law or distribution of the random variable x. A cumulative distribution function, which is CDF, of a multivariate real-valued random variable x with states x, which belongs to the d-dimension space, is given by p of x1 less than or equal to x1, etc., xd less than or equal to xd, where capital X is equal to capital X1 to capital XD transpose, and small x is equal to small x1 to small xd transpose, and the right hand side represents the probability that a random variable xi takes the value smaller than or equal to xi. The cumulative distribution function can be expressed also as the integral of the probability density function f of x, so that integral from minus infinity to x1, etc., integral from minus infinity to xd, f of z1, etc., zd, dz1, etc., dzd. Now let us take the contrast between discrete and continuous distributions. We already saw that probabilities are positive and total probability sums up to 1. For discrete random variables, this implies that the probability of each state must lie in the interval 0, 1. However, for continuous random variables, the normalization does not imply that the value of the density is less than or equal to 1 for all values. This is illustrated in the figure here. We are considering two examples of uniform distribution where each state is equally likely to occur. So this example here is illustrating some difference between discrete and continuous probability distributions. Let Z be a discrete uniform random variable with three states where Z is minus 1.1, 0.3 and 1.5. The probability mass function can be represented as a table of probability values, which is as shown here. 1 by 3, 1 by 3 and 1 by 3. That is the probability when Z is equal to Z for the case where Z is minus 1.1, 0.3 and 1.5 respectively. Alternatively, you can think of this as a graph where we use the fact that the states can be located on the x-axis and the y-axis represents the probability of a particular state. Y-axis in A is deliberately extended so that it is the same as in figure B. Let x be a continuous random variable taking values in the range 0.9 less than or equal to x less than or equal to 1.5. Observe that the height of the density can be greater than 1. However, it needs to hold that integral 0.9 to 1.6 p of x dx is 1. Unfortunately, machine learning literature uses notations and nomenclature that hides the distinction between the sample space, target space, and the random variable. For a value x of the set of possible outcomes of the random variable x, where x is an element of the target space, p of x denotes the probability that a random variable x has the outcome x. For discrete random variables, it is written as p of x is equal to x, which is known as the probability mass function, and it is often referred to as distribution. For continuous variables, p of x is called the probability density function, often referred to as density. The cumulative distribution function for p when x less than or equal to x is often also referred to as the distribution. Now we will see the nomenclature for probability distributions for the case when type is a discrete distribution. Point probability will be p of x is equal to x, which is the probability mass function, and interval probability will not be applicable here. For the case when type is continuous distribution, point probability will be p of x, which is probability density function, and interval probability will be p of x less than or equal to x, which is cumulative distribution function. That's all for now. Thank you for watching.